So for this class, we'll continue on the theme of finding shortest paths in graphs. Okay. And the main goal of this class, or this particular class, is to talk about a famous algorithm called the Dijkstra's algorithm, and it's yet another like shortest path algorithm, but it really exploits the structure of the graph to get a faster algorithm, as we'll see. Okay. Okay, so let's just like recap what we've seen, right? So SSSP stands for like single source shortest paths. Okay. So the problem is, right, I give you a graph, I give you one node called the source, and my goal is to find the shortest paths from that node to all the other nodes. Okay, so that's this SSSP problem. Okay. So previously, right, we saw, okay, if your graph is a DAG, right, you could get this O of m plus n time algorithm, and I'll also write V plus E. So V is the number of vertices, E is the number of E is the edges, but I'll interchangeably use n for the number of vertices, right, and m for the number of edges. Okay. And last time we also saw this like really powerful algorithm called the Bellman-Ford algorithm that says, okay, if I give you an arbitrary graph, okay, it can have both positive weights and negative weights, then in time O of V times E, I can solve this single source shortest path problem. Okay. So this was last time. Okay, so this is not anything new. And now for this class, we're going to assume, okay, what if the weights on the graph are non-negative? Okay, I don't allow the weights to be negative. Okay, they have to be at least 0. Okay, and it seems like a minor change, from having like negative edges to non-negative edges, right? In terms of like, I don't know, you wouldn't think that this would make a huge impact, but it actually does. Okay, so if we know that the edges are non-negative, we can actually get a much faster algorithm than Bellman-Ford. Okay, so that's the point of this class. Any comments, confusion about what happened last time, what Bellman-Ford is, graphs, shortest paths? Okay. All right. So the main point of today's class is we're going to consider graphs, where they can be directed, undirected, whatever, but the constraint is that the weights have to be non-negative. Okay. So that's the main focus. So here's the goal, right? I give you a graph, and every edge has a weight that's non-negative, and I want to solve this single source shortest path problem. Okay. All right. So really, like, you probably like heard about this Dijkstra's algorithm, or if you, many of you, and if you kind of like go online and read about it, it's really mysterious how it works. So one goal for me to show is to show you like it's actually a very natural algorithm. Like this is actually the first thing that you should, if I locked you in a room and I gave you like 10 months to come up with a single source algorithm, this is probably the one you'll find. Okay. So the starting point is to connect back to BFS. Okay. So what's BFS, right? BFS is a graph search again, and the property of BFS was that if I give you a graph with unweighted edges, okay, or the same thing as all the edges having weight 1, then it can solve the single source shortest path problem, right? By starting from a source and kind of decomposing the graph into layers. Okay, so that's how BFS worked, right? I start with a source and I say, okay, I want to partition all the other nodes into layer 1, which is sort of all the nodes that are 1 hop away from the source. Layer 2, all the nodes that are 2 hops away, and so on. Okay. So but now like we have arbitrary weights, right, on the edges, but we still want to simulate the BFS algorithm. Okay, that's the main point of the Dijkstra's algorithm. It's going to somehow like simulate BFS, but in the case where the edges are non-negative. Okay, so we'll see that. Does everybody know, or like everybody remember what BFS is, what it did? Any comments about BFS? Because that's going to be the starting point. Okay. All right. So and having intuition about BFS is like super helpful for having intuition about the Dijkstra's algorithm. Okay. All right. So right, like I said, BFS works great if all the edge weights are 1, right? Or equivalently, all the edges have no weight. And it does it in really fast time, right? The runtime of BFS is O of m plus n, okay? But now let's say I give you a graph, and I promise that all the edge weights are either 1 or 2. What would you do then? Okay. Is there a way to like run BFS on this graph where I promise you all the edge weights are 1 or 2? Right? It's like BFS alone won't work, right? Because now the edges have weight, but I promise you the edge weights are either just 1 or 2. Okay, so maybe like, I give you a graph like this where some edges have 1 and some edges have weight 2. And let's say, one of them is my source, okay? I mean, any ideas like how I would run BFS on this algorithm, right? On this graph? And no, right, BFS can only work on graphs where the edge weights are 1. But now I give you a graph with edge weights 1 or 2. Any ideas about how to like turn this into a nice graph for BFS? Yeah.
Like you could have each layer be like your edge weight. So like all the ones in layer 1 would be from the source that were edge weight of 1, and then all the ones from the source to layer 2 would be edge weights of 2.
So I'm looking for something even like simpler than that. Like, right, I have a graph with edge weights 1 or 2. And somehow, right, I want to run BFS on this graph. But the fact that there are edges of weight 2 kind of hinders me. And I want to turn this into a graph where all the edge weights are 1. Yeah, the guy in the cap. Yeah, so right, one idea is let me just break all the edge 2 weights by, to have the edge 1 weight, to have weight 1, right, in half. So alternatively, right, I'm going to insert like some phantom nodes in the middle, right? And you can say, oh, this node is such that this distance is 1 and this distance is 1, right? This doesn't change like the, if I say, okay, what are all the shortest paths from this blue vertex to all the other blue vertices? Well, that doesn't change anything, right? It's just that now I inserted some new nodes, and now I can run BFS, right? Now I just have a graph where all the edge weights are 1, okay? So you see like kind of how to go from weighted graph to unweighted graph, right? And of course, this should only work, right, if, here it was 1 or 2. But in general, right, like if I have then edge weights that are less than 0, then this doesn't really make sense. But if the, the edge weights are 1, 2, or 3, or whatever, right, then this works. Right, so, right, as I said, if I give you a graph with all the edge weights 1 or 2, I can just pretend like I broke all the edge 2 weights, right, by inserting something in the middle, right, like this, and then now I can run BFS on this graph, okay? But the problem, right, is in general, right, we can't do this for all, even if the weights are positive, right, because the weights could be, like 1/2, right? That wouldn't make sense. Or if the weights could be like some arbitrary fraction, like 1/7, right? It's like not so easy to break it up, right? Or like 2.71 or whatever, right? And also, this is not that nice. Like this transformation is not nice, right? Like if the edge weights can be between 1, 2, 3, 4, 5, and so on, right? Then I'm breaking it into more and more pieces, okay? So the graph is getting bigger and bigger. That's not nice. But this kind of gives you intuition, right? Why BFS is useful for graphs with positive weights. Because intuitively, if you could break the edges into like edges of length 1, then you could just run BFS on it, okay? And essentially, that's like the whole point of Dijkstra's algorithm. It's going to like somehow in the back of the hood, like, or I don't know what the phrase is, but underneath the hood, yeah, that's it, right? It's going to pretend that it's like breaking all the edges into weight 1, okay? All right? So Dijkstra's algorithm is essentially, right, it's doing BFS on this huge graph where like I take every edge of, let's say, weight 10, and I break it up into 10 edges of weight 1, okay? That's essentially what it's doing, all right? Of course, I mean, I haven't given you any details, but this is like some intuition to have in your head, which is, right, we know how to, we know how BFS works, that it works for unweighted graphs. Now to go from like from that to general graphs of positive weights, essentially I can break every edge into, edges of length 1, okay? That's essentially what Dijkstra is going to be doing, all right? So this is all intuition so far. Any comments? Questions? Okay. All right. Oh, that should be an E. Sorry, that's a typo. Okay. So how did BFS work, right? It kind of had this, right? What it did was, right, it took this source node and it layered all the other vertices into, layer 1, layer 2, and layer 3, and so on. And, right, to go from layer 1 to layer 2, right, it said, okay, all the vertices in layer 1, that's my frontier. Now I'm going to relax the edges to go to layer 2. Now layer 2 becomes my frontier. Now I'm going to relax the edges to go to layer 3, okay? Essentially, the same idea works, okay? But we want to simulate this process for weighted graphs, okay? Now, now we're not going to have like such nice layers as layer 1, right? These are all the vertices that are 1 hop away. Layer 2, these are all the vertices that are 2 hops away. Layer 3, these are all the vertices that are 3 hops away. That's not going to be the case because now we have weights on the edges, right? Positive weights. But the same idea works where we're just going to have layers, but the layers are not going to be 1, 2, 3, 4, and 5. It's just going to be sort of like, it's not going to be such nice discrete layers, okay? Like, for example, pretend all the edge weights were either 1 or 1/2, right? Then you'd have a 1/2 layer, which are all the vertices that are distance 1/2 away. Then you have layer 1, which are all the vertices that are 1 away. You have layer 1.5, all the vertices that are 1.5 away, okay? Essentially, you can imagine every edge is like a fractional edge now. And instead of having these nice, like, discrete layers, 1, 2, 3, 4, and 5, we can have layers that are like real numbers, right, or positive numbers. Layer 0.5 or layer 0.7, layer 0.8, and so on. But we can still, the point is we can still order all the vertices into layers, right? So a vertex at layer x is, means that it's distance x away from the source, okay? But we can still order the vertices into these nice layers, okay? So I haven't shown you the algorithm, but right, like the high-level intuition is we're still going to layer the rest of the graph as we did for BFS, but now the layers are not going to be nice numbers, okay? They're going to be like some arbitrary, 0.5, 0.7, layer number 2.2, and so on, okay? Any comments? Yeah. Oops. Okay. And again, right, like if you don't, and if any point you get confused, like you should stop me, okay? Like if you're just staring off into space, like that's not helping anyone. Okay, so so how did BFS work, right? Like to go from layer I to layer I+1, right? I went to all the layer I vertices, and then I relaxed all the edges, right? That went from layer I to layer I+1. Okay, that's how I sort of expanded layer I to find layer I+1. And that's essentially the same. We're going to do the same thing, but now we're going to say, okay, now we're at layer 0.5. Now what is the next layer? We're going to figure that out. Let's say it's layer 0.7. Somehow we're going to relax all the edges from this current layer to find the next layer. Okay. But in your head you can just think like, yeah, it's sort of equivalent to think like, oh, all the edges have weight 1, 2, 3, 4, 5, and so on. But now, or like 1, 1.5, 2, 2.5, and so on. And now I'm just moving from layer to layer. But now the layers are just like not nice numbers. They're fractional numbers even. Okay. All right. Okay. So yeah. Relax. So that was the fundamental operation in this Bellman-Ford algorithm, right? Which is how do I go from, how do I explore new vertices, right? I say I'm at this vertex. I look at all the neighbors, right? So I'll show that in a bit, but I look at all the neighbors and I update their distances, right? That was this relax operation, right, from last class. That's essentially what BFS does, right? It says I look at all the vertices at layer I, and I relax all the edges from the vertices at layer I, okay? So I mean, I'll show more details, but just think like you're maintaining a frontier, okay? And you're saying, okay, to move the frontier, I'm going to relax the edges and go a little bit forward, okay? All right. Okay, so, but now the problem is like, unlike BFS, right? In BFS, we kind of know exactly what the current layer is, okay? It's like all the vertices in my, queue or stack or whatever, right? In BFS, that's the current layer that I'm at, okay? That's layer number I, where, the current layer. So that's like neatly represented, and I can just say, okay, I know all the vertices in my current layer. What I do is I just explore one more layer, okay? But now with having like arbitrary real weights or positive weights, it's not going to be so clear what the current frontier is, right? Like the current frontier might just include one vertex, or for instance, right? Imagine if all the edge weights are let's say 1/2 or 1 again, right? Somehow I want to know, okay, what are all the vertices at layer 2.5 without keeping track of it, okay? So we're going to need some smarter data structure, okay, to kind of simulate BFS, okay, right? And the reason is like we don't know, it's not so clear what the current layer is now, okay, unlike BFS. Okay. Okay. So now let me go into more details of the algorithm, okay? So just to recall the notation, right? We have a single source. Okay, the source is fixed. That's the main vertex I care about, right? I want the distance from the source to all the other vertices. This notation delta s comma v is the distance that I'm trying to find, and then throughout the algorithm, I'm going to maintain some current estimates. Okay, so I'm going to let that be v dot d. That's like my current estimate of the distance to v, right? Distance from s to v. Okay. Okay, so that's the notation that we used last time. All right. So now so I haven't told you what Dijkstra's algorithm is, right? I've sort of tried to build intuition so far, but we're going to need a slightly more powerful data structure than to simulate BFS, right? For BFS, all we needed was this, right? Like kind of this. I mean, you just needed an array, right? And all you were doing was like popping from the front, right? In BFS. But now we're going to need slightly more clever data structures. I'm going to sort of abstract away what the data structure is doing, and later I'll talk about, okay, what are some particular examples of data structures that have these properties, okay? Essentially, I need the data structure to have two main operations, basically this min, delete min. At every point, well, I'll show you the algorithm in a bit, but I need to figure out what is the current vertex with the minimum distance to S that hasn't been explored yet, okay? So I sort of need a way to get to the frontier, okay? So that's what this delete min operation is doing. It's essentially saying what is the vertex at the frontier, right? I know I have a frontier, right? But unlike BFS, I'm not going to explicitly maintain the frontier, but I need a way to quickly access, like quickly go to the frontier, okay? So that's essentially what this is doing. It's going to sort of find the vertex with the smallest distance to S that hasn't been explored, okay? So another way to say it is quickly going to the frontier. And then I need this other operation called decrease key, which says, okay, when I'm at a vertex, right, I need to, what do I do, right? I look at all the edges of that vertex, right? I do this relax operation. Sort of, I need to update the distance estimates of the neighbors. So that's what the third operation is doing, okay? So yeah, I mean, I haven't told you what this data structure is, but I'm just saying I'm going to need a data structure with basically the following two properties. I need to figure out what the current, the vertex that has the smallest distance to the source is that hasn't been explored. And then I need a way to update the current estimates. That's essentially the second and third below, okay? So I'll tell you later, like, what are some examples of data structures that have this property. But have you seen any examples? Like, I mean, it doesn't matter, right? The whole point is we want to do this very fast, but even ignoring that, what are some examples of data structures that have this property that I can do this? Yeah. Yeah, so a min heap works. So probably you've seen a min heap, right? So what is a min heap? Essentially, it's a data structure that allows you to quickly find the minimum. Okay, just think of it as like a binary tree. But it also has a property that you can like decrease the key. And we'll talk about min heaps in a bit. But what's like another more simple example? Well, I can just maintain an array, right? Right, of all the, for every vertex, I have an entry in the array, right? Delete min just means find the smallest value in the array. Decrease key, well, I just go to like, index I, where the ith vertex is, and update the value, okay? So of course, an array also works, right? But different data structures will give you different trade-offs between these operations. So for instance, the an array is really good at this operation, right? It takes me all one time to go to where the vertex is stored. right? It's stored in, vertex 5 is stored in the 5th place in the array. But this min operation is very slow for an array, right? I need to go left to right. But for min heap, both of these operations take log n time. Okay. But yeah, I mean, it doesn't really matter what the data structure we're using, and we'll see that more in more detail in a bit. But I'm just going to abstract away and say I have a data structure that allows me to do the following thing. Okay. And any comments, questions? Dijkstra's algorithm. Yeah, I'm happy to go back if you're lost. Yeah, feel free to ask questions. All right. Okay, so now let me talk about Dijkstra's algorithm. Okay, so this is the boring part. The first part. Okay, I mean, obviously, right? I don't know anything, so all the distance estimates are infinity. The distance estimate to the source is 0, right? I need a place to start. And then I'm going to build this data structure priority queue, okay? So that's the boring part. Now, what is the main loop, okay, of Dijkstra's algorithm? It's very clean, okay? So this is the entire algorithm, okay? So just imagine how BFS or Bellman-Ford is working. It's almost the same. So the main loop is following. While I haven't explored all the vertices, okay, that's going to be, I'm going to keep track of that by this priority queue. I'm going to find the closest vertex to the source that hasn't been explored, okay? So that's this U, right? So initially, right, the first thing that gets popped out of this priority queue is this S itself, okay? Because everything is infinity, S is 0, okay? So essentially what U is the closest vertex to S that I haven't explored. In other words, it's the vertex at the frontier, okay, of my current frontier. So I immediately go to the frontier, okay? And then at the frontier, what do I do, right? I need to explore one step more, right, at the frontier. I need to grow the frontier. What I do is I look at all the neighbors of this vertex, and I do this relax operation, same as Bellman-Ford, right? Right? What do I do, right? It says, okay, if the neighbor has a distance estimate that's larger than going to U plus taking the edge, then of course I'm updated, right? Same as Bellman-Ford. And then I need to decrease the estimate, and then I keep track of that using this priority queue. All right. So it's working just like BFS, but it's sort of maintaining this BFS structure in an implicit way. Okay, it's not maintaining the exact frontier every time. It's just saying at every step I can go to the frontier by popping out the minimum vertex, the minimum distance vertex that hasn't been explored. Right? That's imagine how this works in BFS, right? Where all the edge weights have weight 1. The first thing that gets popped out, right? All the first vertices is like all the things that are at distance 1. All of those will get that will be all the U's that get popped out first. Then all those U's will update, right? They'll update their neighbors. Then all the 2's will get popped out. Then all the 3's will get popped out. But now, right? Now we don't have such nice, integer numbers. We can have like 0.7, 0.3, 5.7, 16.9, like all these random numbers, right? But this, q dot delete min is going to go to the frontier, okay? It's going to pop the vertex that's the closest vertex to the source that hasn't been explored, okay? So it's like it's an instructive exercise to say, okay, if I run this loop in an unweighted graph, what will it do? And it will do exactly like BFS. It will pop out first it will pop out the source, like BFS. Then, right, the source will update, right, to all the one-hop neighbors. Then all the U's that will get popped out in this delete min will be things that are one hop away. Then I'll pop all of them out first, okay, just like BFS. Then, then the things that will get popped next will be the things that are 2-hop away, right? And then the 3-hop away and the 4-hop away. So it'll do exactly the same as BFS, but now it's maintaining this frontier, right? This frontier with arbitrary positive weights, exactly, in some implicit way, okay? So this is Dijkstra's algorithm. Any comments? Questions? Yeah, and then of course, we'll see how it works in a bit, but at least does the the description of the algorithm makes sense, right? So this is this relax operation, right? I'm saying, if it's the current estimate to v that I have is worse than going to u and taking this edge, then of course I'm going to update it, okay? Yeah. Yeah, so, right, so this is the weight of the edge. Yeah, weight of the current edge. Yeah, so it's the, all I'm saying is I go to the frontier, I look at all the edges coming out of u, right? And then this is the weight of that edge. So I'm saying if the current estimate that I have to v is worse than going to u and taking this edge, right, and paying this weight, then of course I'm going to update it. Yeah, so that's this w. Questions? Dijkstra's algorithm. Okay. All right. So let's see how it works. Okay. All right. So yeah. Sorry, I got this from somewhere else. So this d should be this delta. Okay. This is the distance. Okay. But whatever, you can figure that out. So now let's see how it works. Okay. So this is my graph, and let's say the source is a. Okay. That's my. I want to find all the shortest paths from A to the rest of the vertices, right? All the weights are nice and positive, okay? So of course, the first vertex that gets popped out, right, in this priority queue is itself. Everything else has infinity. I have 0 at A, right? So of course, that pops out. And then what happens, right? Then I look at all the edges, right, going from A, and I say, oh, okay, I can update the distance to B in this priority queue. It goes from infinity to 1. C gets infinity to 1. D gets infinity to 3, right? Then what is the smallest, right? Then I do the next pop operation. It's B, right? I pop out B. And you can see like this frontier is growing, okay? And then I relax all the edges of B, right? I relax BE. Right now, E was infinity, but now it's 5, right? B plus 4. I can go to D now, right? D gets 2. And then I pop the minimum, right? Minimum is still C, right? And then I pop the minimum, okay? And then, okay, what's then the next vertex? Okay, so it's just D, okay? And then E, and then F. Okay, so we'll see another example. So here it was like in order. Okay, so we'll see another example. Okay. Now the source is called S, okay? So call the source. And now I have, let's say, a directed graph even, okay? Right? Initially, the priority queue is this, okay? Everything is infinity except S is 0. So what is the first thing that I pop? Well, I just pop S, okay? And then I relax all the edges from S, okay? What does that mean, right? That means all the distance estimates, from S to all of its neighbors, right? B, C, and D get updated, right? So it's like 0 plus 2, 0 plus 6, 0 plus 6. Then I pop the next minimum thing, right? So the grayed out means it's already been removed from Q, okay? Then I pop the next minimum, which is B now, right? Then I relax all the edges from B, right, to C and E, right? I pop out B, and now B is gone. Okay, I can never remove B with B again. And then I say, okay, next smallest is C. I remove C. But now, right, it's not D, now it's E, right? E has 4, so I pop that out. And finally, right, so look, right, E causes the distance to D to update, right? Because currently E is at 4, and there's this edge of length 1, right? So when I pop out E and I relax all the edges going out from E, right, D gets, well, D currently has 6, but I would rather go to E, which takes 4, and then take this one edge, which will cost me 5, right? And then D, when D pops out, there's nothing to do in the rest of the graphs. Okay, so now then this is the complete, all the distances from S to all the other nodes, okay? Any questions about like how this ran? Yeah.
So when you were talking about like the fractional layers,
yeah.
How does that relate to this example?
Yeah, so this example is sort of nice, right? There's no fractions, but kind of what's happening is like, right? Imagine I do BFS, right? First I need to go to layer 1, but there's no layer 1 here, right? So now I immediately go to layer 2. Okay, so that's at B. And there's no layer 3, so I immediately go to layer 4. So if there were fractional values, maybe I have another example. Maybe I did fractional there, but for an instance, right? Let's just make something up. Let's say this edge was not 2, but it was 1.1. Okay, then it will still pop B, right? And then it will pop, right? When it pops B, right? When it updates C, it won't be 4. It'll be like 3.1. Okay, then that's the layer. That's layer 3.1. It will immediately pop C. So instead of 4, this will be 3.1. But yeah, that is a good point. Like, yeah, I mean, this example doesn't have fractions because I was trying to find a nice example. But in some sense, it's like it's going to skip all the layers that are not important. Okay, there's no layer 3, 4, 5, whatever. But if there's layer 17.7, like some vertex is at distance 17.7, it's going to immediately go to that layer by popping the minimum. Okay, so it's not like BFS where it like kind of enumerates all the layers. Kind of Dijkstra automatically goes to the next sort of next relevant layer automatically by popping the minimum. Okay. So I have one example. Oh, okay. This one also doesn't have fractional weights. Okay. Whoops. But like maybe an instructive exercise to go home is, so I'll go through this example, but kind of change some of the values, maybe even implement it yourself, and then see how like what the next vertices are and so forth. Okay. So let's do one more example. Here there's no animation, but I'll kind of like walk you through it. Okay, so the first vertex that gets pop is S, and at that point, right, everything is it's the top row, right? Everything is infinity except S is at 0. But then when I pop S, right, I get to update these two edges, right? I get to relax. So then C becomes 3, and A becomes 10. Then what is the minimum, right? It's C. So then I pop C. All right, I delete C. And then I get to relax all the edges going out from C, right? So I relax this edge, I relax this edge, I relax this edge. And then things get updated, right? Initially, A was at distance 10. But right, I go from 3 to 4. That's better. So I update it to 7. Initially, D was infinity, right? But when I pop C, I can go 3 to 2. So it becomes a 5, and so on. And then I pop the minimum, which happens to be D, and then I relax the edges from D, and then then the minimum becomes A finally, and then becomes B, and so on. Okay, so what is sort of implicit in this algorithm is every time you remove a vertex, that vertex is done. Okay, that's kind of what we'll prove, and that kind of has to be the case, right? Because if I remove a vertex from this priority queue, it's never looked at again. Okay. It's just gone, like the algorithm has no idea. So it better be the case that when I remove something from this priority queue, then I'm done with that vertex. And that's essentially what's going to happen, right? So look, right, the first thing I removed was S, obviously, right, S to S is 0. Then the next thing I removed was C, okay? And when I remove C, right, my estimate was 3. And indeed is the case that, distance from S to C is 3. Maybe another better example is D, right? When I remove D, my estimate is 5. Okay, and that is indeed the best way to go from S to D of cos 5. Okay, so whenever I remove something in Dijkstra, implicitly I'm saying I'm done with that vertex. I've already explored, I've already found the shortest path from the source to that vertex. Okay, and we're gonna prove that. But yeah, any questions about how it works? So essentially, right, I'm just maintaining you don't even think about this priority queue. Okay, it's just imagine a table. Okay, I'm maintaining the distances from S to all the other nodes. Some of the values might be infinity, okay? I just always pop the one that's the minimum value, and I relax all the edges going outwards from that pop vertex, okay? And then that causes me to update some other values, and then I find the new minimum. That causes me to update some other values, to find new minimum, and so on. Ultimately, right, every vertex is removed from this priority queue, right? We've kind of marked out every vertex, and every time we mark something out, then implicitly we're saying we're done with that vertex. Okay? And at the end, like, we'll have a bunch of numbers, and the claim is like these numbers will be the shortest path distances. And to actually construct the shortest path, you can just keep track of these parent pointers. Kind of like, okay, what caused me to update to this value? Just remember those, right? In the description of Dijkstra algorithm, right, I have this parent pointers, kind of this pressure tensor whatever caused me to update, if you remember that, you can also construct the path that way. But for now, let's just focus on the value, okay? All right. Any questions about how this works, how Dijkstra's algorithm works? I mean, it might still be mysterious why it works, and we're going to get to that shortly. But at least how it works, does that make sense? Questions? Yeah, I'm happy to go over the examples again. So feel free to ask like that. That's okay. Okay, but right, another way you can think of it is just like it's just doing BFS, but now like you have fractional weights, right? Another way to think about it is like let's say I have weights that are that have one decimal point, like they can be 0.1, 0.2, 0.3. Just imagine multiplying all the weights by 10, so it's integer, breaking all the edge weights into one, and running BFS on this graph. That's exactly what's happening. Okay, that's another way to think about it. Questions? Okay, so now let's show why why Dijkstra's algorithm works. Okay. Right. So what we need to show is when the algorithm is done, we found the right values, right? That's the main thing. Otherwise, why are we doing this? Yeah, essentially, right. So this is not saying anything interesting. Essentially, right, all these words are saying is what we're going to show instead is the following. We're going to show every time a vertex is removed from this priority queue, then at that moment, I found the right distances to that vertex, okay? For that vertex only. I don't know about other vertices that have not been removed, but at the point where I remove a particular vertex, I'm done with that vertex, okay? So that's essentially what we're going to show. And of course, right, at some point, I'm going to remove all the vertices. So of course, I'll be done with the whole graph. But the main loop is showing that anytime I remove a vertex, I'm done with that vertex, okay? So that's the main claim. Okay. Anyone remember how the proof of BFS worked? Essentially, the proof was like, well, if a vertex is at some hops away, like hop 10 away, I do induction, right? I say, OK, I'm correct up to hop 9. And of course, if a vertex is hop 10 away, it must be a neighbor of a hop 9 vertex. So that's when I'll find it. OK, so that was the proof. So essentially, the proof is going to be the same. OK, we're going to say that, right? So we're going to prove it by induction. That's why, I mean, induction is really powerful, right? It's like you almost don't do any work and you get something for free. So we're going to show, right, by induction that every time a vertex is removed, we're going to have found the right answer for that vertex, okay? So the base case is obvious, right? The base case is, okay, I just pop the first vertex, S. It's at distance 0, okay, from itself. There are no negative weights in the graph, right? So 0 is the best, right? So, okay. Now we're going to assume, okay, now imagine I'm at some intermediate run of the algorithm, right? Now I have to show this induction hypothesis holds. If everything is correct so far, then the next step will also be correct. That's the main point of induction, okay? Right, so now assume I remove some vertex from the priority queue, right? I want to show that vertex is done. And how do I show that, right? I'm going to assume that all the vertices that were removed before are done, okay? So that's my induction hypothesis, right? If I assume everything before is done, then the next step will also be done, okay? That's essentially what I'm showing. Okay, so now, I'm going to have to draw some things, okay? So the proof is very slick, okay? The proof is not, it's like only a few lines, but we're going to have to think a little bit, okay? Okay. So now I'm at this vertex V, right? I just removed V from this priority queue, okay? I want to claim that when I remove this vertex, I've found the shortest path from S to that vertex, okay? Or the shortest path distance, let's say. So let's imagine the best path, okay? And pretend it looks like this, okay? It goes from S all the way to V, okay? In my head. I'm just imagining this in my head, right? I'm just proving. I don't know what it is, right? But I'm just imagining, right? Some path exists. This is the shortest path, okay? And I'm going to let Y be the first vertex on this path that was not removed yet, okay? So Y could be V, for instance, okay? So it's like right before the moment where I remove V, I consider the shortest path, okay? It goes from S to V, and I'm going to let Y be the first vertex that was not removed yet from this path, Okay, so y could be v, for instance, right? Because I haven't removed v yet. I'm considering the time that's like right before I remove v. Okay. All right. So this is all in my head, right? This is all in our head. We're just imagining what the best path looks like. It has some vertex, right? The first vertex on this path going from S that was not removed yet. Okay. So of course this y, I'm just like, it's like a hypothetical thing that we introduced, but we're going to use y to argue that when we remove v, it's going to be correct. Okay. So this is like, okay, it's going to be very slick. But so far I haven't said anything, right? I'm just saying, imagine the best path, and let y be the first vertex on this path that has not yet been removed, and y could be v. Okay. So I haven't removed v yet, right? I'm considering the time where I just right before I remove v. Okay. So there must be some vertex. I'm going to call it y. Okay. All right. Because y is the first vertex that has not been removed yet, x was already removed. Okay. And x could be s, for instance. Okay. So I'm just saying on this path that goes from s to v, the best path, there has to be some first vertex that has not been removed yet. I'm going to consider the vertex right before it. Okay, that's called x. And by induction, okay, whenever I removed x, so x could be s, for instance, right? I don't know. I'm just saying there's some two vertices, right, where I go from removed to not removed, right? It could be s, or it could be all the way to v. I don't know. But I do know that whenever x was removed, right, it's already been removed, it was correct by induction. Okay, that's the induction hypothesis that I'm using, right? So that's why like x could be s, for instance, right? Let's just say the path was only like one hop, then right, there's no x and y, there's just s and v. Okay. But just in the general case, imagine the path was really long, and there's some point, right, where you go from removed, not removed, right? All right. Let's consider the first step, first time that happens. All right. Okay. Now we go back to in our head and say, okay, what happened when x was removed from this priority queue? Well, I updated the edge x comma y, right? That's how it works. I relaxed that edge. That means I had to have updated the distance estimate to y. Okay. And the claim is that, okay, at that point, I had the right answer for y as well. Why is that? Well, right, at some point I removed x from the data structure, from the priority queue. I relaxed its edge. And it must be that at that moment, I was already done with y, even though I haven't removed it from the data structure. And the reason is that S to V is the best path, the shortest path. So everything in the middle must also be the shortest path to all the intermediate vertices. That's where we're using the fact that the edge weights are non-negative, okay? Right? Because I know that S to V is the shortest path that I've drawn, this must also be the shortest path to go from S to X and S to Y, okay? Because otherwise I would just have a different shortest path to V, right? If there was a better way to get to Y, okay? So that means when X was removed from the graph, from the data structure, and I updated the distance estimate to Y, I was already done with Y, even though I didn't realize it, okay? All right? So that's what this is saying, right? At some point, I removed X, I relaxed its edge, and I was already done with Y, okay? But I know that the distance from S to Y is smaller than the distance from S to V, okay? And that's again because they're all on this shortest path, right? They're all on they're all on the shortest path, and all the edge weights are non-negative, okay? That's again another place I'm using the edge weights are non-negative. I mean, so far I'm just writing like a series of inequalities, and they were like, okay, well, what does this have to do with anything? But we're going to show the final step, okay? And the final step is the following, okay? Or there's one more step. But right, why do we remove V, okay? Or sorry, right? I know that the estimate to V can be better than the actual distance, okay? So that's just obvious, right? This is the estimate the algorithm has. It can never be better than the true answer, okay? But now here's the catch, right? Why did we remove v instead of y? We removed v instead of y because v was the minimum value in the priority queue, okay? Okay, so that means you get this final inequality, okay? So we started with the distance to y, okay, to this like hypothetical node in this path that we introduced. Then we argued that when the node right before it was removed from the priority queue, I was already done with this node y. But then, right, I popped v from the data structure, not y, right? That's how v was defined, right? It's the next vertex that was removed. But I popped it because, right, how does the algorithm work? Well, it pops the things that has the smallest estimate. So the estimate to v must be smaller than the estimate to y. But look, this y dot d, the estimate to y is on both sides. Okay? So that means all the inequalities in the middle must be tight. They must be, they must be not inequality, but they must be like all the same, right? Equal. And right, look, that means this estimate is equal to the true value, because I'm squeezing something by the same thing on both sides, so they're actually all the same. Okay. So it's a little bit like mysterious, right, what happened? But let me just give you a high-level idea. Essentially, we're using the fact that we popped v instead of y to argue that like everything in the middle must all be tight. All the estimates must be correct. Essentially, that's what we're doing. Okay. And of course, right, v could be y, so that's why then that's also fine. That's a edge case that you can think about. But like I said, right, at a high level, what we argued was the following things. Okay, we said, okay, subpaths of shortest paths must also themselves be shortest paths. That was very key. And then the other key thing was like in a graph with non-negative weights, having a longer path can only hurt you. Okay, that's the second key thing. And somehow we used those two facts to argue that when we popped v from the data structure, we're actually done. And the reason is, right, well, there's some node in the middle that we haven't popped yet. But why do we choose to pop v instead of that node? Well, it must be that like everything in the middle was already done, essentially what we're saying. Okay. Yeah, so it's not like a difficult argument. Like we can follow step by step. But the magic is really like saying, oh, look, where we started and where do we end. That means we're all already done. Okay, so that's the kind of the cool fact. Okay. But if this confused you, like it's that's okay. Just think the proof is the same as the BFS proof. Just imagine we're running it on this hypothetical graph where all the edges have been broken into length 1. Okay. All right. Yeah. Any comments about the proof? Questions? Yeah. Yeah, I guess in the test, it'll be more like, use Dijkstra in a clever way to solve some problems. So, but kind of knowing why it works always helps with that. But yeah, I mean, I guess like, if you don't like the proof, you don't have to study it. That's okay. But it is pretty cool. That's the point. Okay. Questions? Yeah, if it didn't make sense, I'm happy to talk about it again. But right, like I didn't use any very difficult argument. Like going line to line made sense, but somehow, right, we ended up with where we started. So that means everything was correct. That's the magical part of this proof. Okay. All right, now we know that the Dijkstra's works. We need to answer, okay, how fast is it? How fast is it? Okay, so the whole point was like, hopefully it's faster than doing Bellman-Ford, right? Bellman-Ford was m times n. Hopefully we can do much better. Because the proof really exploited the fact that the edge weights are non-negative, okay? Like this proof, if you try to think like, where does this proof break down in a graph with negative weights? That's also an instructive exercise. You'll notice like there's a couple of steps. Or like, in a graph with negative weights, it may be that taking a longer hop path actually could be better. But that's never true for a graph with non-negative weights, right? I can just like, if I have a path and I add more edges, the path only gets worse, okay? Because all the edge weights are non-negative, okay? You're just adding like positive numbers to something, so it's always going to be bigger. Okay, so now let's talk about the running time. So the running time really depends on like what underlying data structure we're using for this priority queue, right? So what is this priority queue doing? It's basically like, right, you can imagine every node has a number, okay? I'm updating some numbers. I'm always decreasing some numbers, right? These are the distance estimates. And I'm deleting the smallest number every time, okay? Yeah, I mean, there are many ways to do that. So let's just see, right? And this will give you different running times. But really, I can sort of abstract the running time away in terms of the following, right? How many deletions I'm doing? Well, I'm doing n deletions, right? There's only n nodes. And how many, these decrease key operations I'm doing? Well, I only do it once per edge, essentially. So I'm doing it m times or e times, okay? So essentially, if like whatever data structure I'm using for this priority queue will directly lead me to some running time. And there are a bunch of choices, okay? So there are a couple of choices, okay? So the first one is, okay, I don't do anything clever. I just keep everything in a list, okay? So what is a list, right? I just have a list of n numbers, one for every node. And how much does delete min cost? Well, I have to scan the array, right? The array is just a bunch of numbers, so it costs me n time. But to decrease a value, that's all one time, right? Like if it's a vertex number 5, I just go to the 5th index of the array, and I decrease that value, okay? That's all one time. And if I plug it in, right, that will take me n squared time, okay, if I use an array. If I use something called a binary heap, so maybe you've seen binary heap, maybe you haven't. But if you haven't, like, it's a very fundamental data structure, so you should like just Google binary heaps. But essentially, it's like a binary tree that helps you figure out what the minimum is. It's a little bit more than a binary tree, but you can kind of think of it as that. But essentially, every operation in a binary heap, at least these two operations take log n time, because you have this balanced tree, right? You can imagine, okay, it's a balanced tree, it takes log n time. So the finding and deleting the minimum takes log n time. Decreasing a key also takes log n time. And if I plug that in, I get e log v, okay? The number of decreased key operations kind of dominates. And now there's this like crazy data structure called the Fibonacci heaps. I'm not going to talk about it, and maybe you never have seen Fibonacci heaps. You probably never see Fibonacci heaps. They're very complicated, but like at least mathematically, they're like the best data structure to use, okay, for this problem, because every delete min will take log n time, but every decrease key takes only constant time, okay? So these are some really crazy data structures. And then if I plug that in, I get e plus v log v, okay? So if you look up the runtime of Dijkstra's algorithm, it's usually going to be written as e plus v log v if we use this like super optimized heap, okay? But if you actually wanted to code Dijkstra's algorithm, like you should probably just use a binary heap, okay? Not this Fibonacci heap. And actually, like if you ever look up Fibonacci heap, like implementing is actually it's actually very fun. So you should try that if you want. Yeah, but for the sake of this class, like you can just assume Dijkstra's runs in this running time, okay? E plus v log v, okay? Right, and let's compare that to Bellman-Ford, right? Bellman-Ford was e times v, okay? So it's like instead of multiplying these two quantities, I'm adding it, right? So it's a much smaller value. So it's much, much faster, right? Imagine like I have a graph with 1,000 nodes, and e is close to like million, right? Then instead of multiplying 1,000 by million, I'm essentially getting million, not like a billion, okay? So this is a much faster algorithm, and if you know your graph has non-negative weights, you should use this, okay? Okay, so just to summarize, right? This is sort of the end of the single source shortest path algorithms, right? So if you have an unweighted graph, BFS is great. If you have a DAG, but with weights, you can use topological sorting and one round of Bellman-Ford. if you have a general non-negative graph, right, then Dijkstra's algorithm is great. But then if you have a graph with possibly negative weights, then you have to use this Bellman-Ford algorithm. Okay. Okay. Any questions about this table or the running time of Dijkstra's algorithm? Okay. So now here's kind of one interesting point, which is like, right, something we glossed over is, right, the way I defined the problem was I give you a source, and I want to find all the distances from the source, from the distance from the source to all the other vertices, right? And you might say, like, okay, what if I'm only interested in one pair? Then that's like the funny thing, which is finding distances to one pair turns out to be no easier than finding distances from one to everything, okay? So there's no known faster algorithms if I just care about one pair, okay? Somehow, like, this single source path is the problem you care about. Finding everything is actually just as easy as finding one pair, okay? But in practice, it can make a difference. So in practice, what people do is, like, I mean, usually, right, the graphs are non-negative weights, and I only care about, let's say, one pair. In practice, what people do is they do this thing called, like, bidirectional Dijkstra's, where essentially, if I'm only interested in one pair, I do Dijkstra's in alternating turns from each node. And then if the two frontiers ever meet, meaning, right, I have two priority queues, if I've ever, like, deleted a vertex from both of them, then I know I'm done. Okay? That means, like, the frontiers have met the first time, and then, right, I found the shortest path. So, you know, oftentimes I can be like a factor of 2 faster because I'm finding it from both sides. But asymptotically, it's not faster. Okay? Yeah, any questions so far? Okay. Okay, so now next time we're going to solve this slightly harder problem called all pairs shortest paths, which is essentially I don't want the distance from one node to everything. I want distance from every node to everywhere else. Okay, so that's why it's called all pairs. APSP, okay, all pairs instead of SPS or single source shortest paths, whatever, right? Well, right, the only algorithm we know that works for general graphs is Bellman-Ford, right? And the most naive thing to do is you run Bellman-Ford from every node as the source, and that takes O of v squared e time, right? You know, with a graph with negative weights, for instance. But if I know that the graph has only positive weights, right, I can instead do Dijkstra's from every node, and that's like a O of n time, O of v time overhead, right? This times the regular running time. Now, the cool thing about all pair shortest path, it turns out, which we'll see next time, is even if your graph has negative weights, you can get the above running time if I want to solve the all pairs version. Okay? So for a single source, I need to pay this Bellman-Ford. There's no known faster algorithm. But magically, it turns out if I care about all pair shortest paths, I can somehow reuse computation in a very clever way and get this. I can sort of pretend like the graph only had non-negative weights, and I'll get, I'll show you that next time. Okay, it's called Johnson's algorithm. But that's kind of cool, right? Like somehow this all pairs shortest path is not necessarily running n versions of single source shortest path. There is some savings that I can do if I know I'm solving this much general problem. Okay, that's cool. Yeah, so I think in the last 10-ish minutes, yeah, let's think a little bit harder about Dijkstra's algorithm. Okay, so let's see. Can someone give me an example of a graph with the negative weights where Dijkstra's algorithm won't work? So let me go to the board. So while you think, let me quickly. Yeah. Anyone have like a? I mean, just whatever you think of. Like, it doesn't have to be correct. That's okay. Yeah. Yeah. Yeah, but let's just say I want to do something super naive, like I know this graph has negative weights, but let me just run Dijkstra's algorithm and see what happens, right? I can do that, and I'm looking for an example where, like, if I look at the final values at the end, it won't be correct. Yeah? Yeah, something like that, right? So essentially the proof of Dijkstra's algorithm, it really used the fact that like shorter paths are better because things are non-negative, right? Like if I have a path from S to V, and like if I add more edges on this path, like it's not going to help me, right? Because I'm only accumulating, let's say, positive edges. So yeah, so the simplest example looks something like this. Let's just say, okay, so let's just make something up. Okay, so let's say this is the source. Let's just say this is 1, 3, minus 10, minus 100, okay? All right, so we'll just call it A and B, okay? So let's say I run Dijkstra's from the source, right? The best way to go from S to A is this way, right? Right, I get 3 minus 100, that's minus 97. But right, what will Dijkstra's do, right? It will say, oh, okay, right, pop S, relaxes edge, that's 1, that's the minimum, I pop it, I'm done. Right, so you can kind of see like where the proof is breaking down, right? Like, right, the main claim of the proof was when I popped a vertex, I'm done, right? Here it's no longer the case. Okay, so this is one example. Okay. What was I going to say? Yeah, and then it's instructive to see like how even if you didn't understand the proof, like where in the steps things break down. Like we're really exploiting the fact that things are non-negative. Let's see. Did I have anything else to talk about? Yeah, I think that's it. Oh yeah, sorry. Go ahead.
Could you explain that part again? Like when you pop A?
Yeah, so right, so how does the Dijkstra's algorithm work? So initially, right, S is at 0, everything is infinity, and then right, I pop S, and then I relax the edges, right? I relax this edge and this edge. Right? So let me just kind of kind of draw it out. S, A, B, right? Initially 0, infinity, infinity. I pop S. And then, okay, it says 0, and then A gets 1, B gets 3, right? I'm done with this. Then I pop A. Well, and then, right, nothing really happens because A doesn't have any edge. And then I pop B. But, right, at this step where I remove A, right, the main claim on the proof was anytime I remove a vertex, I'm done. That's like obviously not the case here, right? If when I remove A, my estimate was 1. But that's not the best way, right? The best way is this way. Yeah, so this is just to show you that like if I literally follow Dijkstra's algorithm step by step, the main claim, which is when you pop a vertex, you're done, that's not true. Yeah, and I also like recommend you to go home and implement Dijkstra's yourself. It doesn't have to be super fancy. Like just use an array if you want, and then see how it's working in the graph. That can always be helpful to build intuition. Yeah. Other than that, I'll be here to answer any questions. But yeah, that's it. Thanks.